Okay, let's talk about the seashore for a second then with convection as well. So as it shallows and comes up on the beach, and that's kind of where you're standing here, on the beach, we have our water. We make it a choppy day. Okay. So what happens with this? Why does a breeze occur here coming off the water? What we have is we have the very hot sun heating up the sand, making the sand very hot. That's why you're hopping around looking silly. But what happens is the air that's over the sand gets heated and heads upward. Okay. Again, we had this void then that's created. So we have cool air that has to move in here to take up that spot. So cool air, here the air gets heated. What happens is the air rises into the atmosphere here. All right, the air gets cooled because up higher, the air is cooler. So that red then becomes a blue, which falls back down over the water. And this is essentially causes that, we'll call it the sea breeze here. All right, so convection results in that sea breeze. All right, and it's just that the heating and cooling process and creating voids and moving that air from one location to another. Third and final one is transfer of heat energy through electromagnetic radiant energy. So I'm going to probably simplify this a little bit because we haven't talked about and don't talk about electromagnetic waves until grade 12. So let's keep it simple at this point. What is the heat lamp? It used to be in all the fast food restaurants, right? Where the food would sit under it. And some of the current smorgasbord restaurants, I guess, still have it. They have this red light. The reason for the red light is it creates electromagnetic waves. And we're going to talk about this in the grade 12 course. Electromagnetic waves then excite the molecules or atoms and will heat solids or heat material. So there's my hamburger. Put a hot dog package on there. So the waves heat the food by, and I'll just say by exciting the atoms. Okay? So those electromagnetic waves pass energy through that process. And like I said, I'm not going to go into a whole lot of detail. You just have to tell me. A heat lamp's an example. Microwave ovens use it as well. Basically, don't ever put your jump drive inside the microwave. I wouldn't recommend putting anything but food in the microwave, of course. But what happens? There's magnets inside the microwave, and coupled with electricity, what happens is put a turkey in there. There's the drumstick. There's the rest of the turkey. Okay. Electromagnetic waves are produced via electricity and magnets. What it does the exact same thing. Okay, so you can put that down there as well. So it excites those atoms to vibrate back and forth, and by doing that, it heats up your food. Okay, it excites the atoms so that they vibrate, and that energy then is transferred as a heat transfer. So there is your radiant energy. All right, radiation. So there are your three forms. So let's talk about some of the math behind this. So let's talk about, it's called specific heat capacity. If you haven't come across it in chemistry, you will. But heat transfer depends on three things. Okay, we're talking about, first one's a temperature difference. So what is the difference between what's being heated and what's being used to heat it? How much of the substance are we going to have to heat? And finally, the type of substance, because everything heats at a different rate. Specific heat capacity, so not a definition you're going to have to regurgitate, but you need to be able to identify or understand what it means. It's how much energy, so the amount of heat energy that is needed to increase the temperature of 1 kilogram of a particle substance 1 degree Celsius. So how much heat energy is required to move 1 kilogram of turkey 1 degree Celsius. So here's our formula. And it's another energy formula. So it's MC delta T, where M is our mass. So put the legend down. M, mass. of substance. C is your specific heat capacity. And that has to be given unless you're looking for it in the question. It's got to be provided because every material is different. And finally, T is your temperature, obviously. Okay, so there is that formula. You want to make sure this gets added to your cheat sheet with your energy formulas. So let's do a couple of examples here. So how much heat energy is required to heat a piece of gold from 25 degrees Celsius to 50 degrees Celsius? So we're talking about heat energy here. So we have our EH equals MC delta T. So we're looking for how much heat energy. So how much heat energy is required a piece of gold, so we don't know. So I'm going to leave it as M. Specific heat capacity is given. That's joules per kilogram Celsius. And the delta T is 25 degrees. So when you do this calculation, and this is why mass is often not given in the questions. So when I do the calculation here, times 25, I get 3,250 M joules, or you can report this as 3,250 joules per kilogram. Okay, so it depends on how many kilograms of gold. Regardless, for every kilogram, I'll need 3,250. So therefore, you need 3,250 joules for each kilogram of gold. Oops. Okay. So that's why mass in a lot of the questions isn't provided or isn't given. So 0.75 kilogram block of aluminum at 90 degrees is cooled by removing 5 times 10 to the 4th joules of heat energy. What's the final temperature of the aluminum? So with this one, the only thing you need to remember is that this delta T, and I'm going to throw the extra step in here, is also, if we go back a page to your formula, T2 minus T1. Okay, so T2 minus T1. So the unknown then is that final temperature, and that's the T2. So that's what we're really looking for, which means we should have all the other information. So I know that I took out 5 times 10 to the 4th joules. I'm given a mass this time. Specific heat capacity. Okay. If you look at the comparison between gold and aluminum, aluminum has a much higher specific heat capacity, which means it takes more energy to heat up aluminum than gold. All right. So 9.1 times 10 squared multiplied by T2 minus 90. All right. Now it's just math from this point. So isolating, so at 5 to the 1 to 4, I'm going to divide it by the 0.75 times 9.112. So I'm going to end up with an intermediate value. It looks like this. And when I go to solve, I end up with a much higher value. And the reason for that is this. Heat was removed. Heat was removed. So therefore, EH is negative. All right, so if you're taking heat away from the system, it's being subtracted away, so I should have had that as a negative number. So not a big thing to change here. So the negative goes in there, which makes a whole lot more sense for us here. And so the 73.3 plus the 90 now. So we know the new temperature then, T2, is equal to 16.7 degrees Celsius. So therefore, it ends at 16.7 degrees Celsius. All right, so there we are. Here's the homework. Okay. that will give you a taste for what to expect. If you have any questions with any of the calculations, let me know and we'll get them cleared up. Okay, good luck.